Hello, good morning, good afternoon, and good evening to everyone who's tuning in. Hope you're doing well and staying safe. On behalf of Petro, Arab Oil and Gas Academy, SPE Egypt section, I'd like to welcome you all for today's long-awaited session. I'm Mayar Tariq, a third-year gas and petrochemical engineer student at Alexandria University, and I'll be your moderator for today's session. Before we start, please, I'd like to remind you to drop your questions in the Q&A section below. Please keep the chat box professional and ethical. And please don't forget to submit your quizzes before the deadline. Now let us give a warm welcome to our top-rated Professor Dr. Moustafa Oraby, who will give us a session in shale gas evaluation and development. Dr. Moustafa Oraby has a 25 years experience in petroleum industry. He holds a PhD degree from North Carolina State University in the United States and a master and bachelor degrees from Alexandria University. Dr. Moustafa also joined Alexandria University in his early career as an assistant lecturer till he obtained his master's degree. He also used to teach at community colleges in the United States. In the industry, Dr. Moustafa held many positions in all aspects of petroleum industry and lived in many countries around the globe. Dr. Moustafa Oraby, thank you so much for coming, and the mic is yours.
Thank you, Mayar, very much for this nice introduction. And without any further ado, guys, we'll start our lecture today on shale gas evaluation and development. I just like to set the stage to remind you a little bit of what are the shale gas that we discussed before in a previous webinar. So the content of this lecture today, it will be actually divided into three sections. The first one is the evaluation. Then we'll talk about development. Then I will leave few minutes for the question and answers. Okay. For the evaluation part, we'll have a quick overview of the unconventional reservoirs very quickly. I ask everybody before just to go and review or listen again to the previous lecture, just to remind yourself what are the unconventional reservoirs. Okay, we'll have a very quick overview of this webinar. Then we'll talk about the conditions for unconventional gas reservoirs. When can I call an unconventional reservoir a gas reservoir? Is there any indications? How do we know that? How we differentiate between gas reservoirs and oil reservoirs from the unconventional point of view? This requires a lot of attention, guys. So please make sure you pay attention to this, take notes. And if you have any questions at the very end, I'll be more than happy to answer these questions, because we will talk about absolutely different concepts than what we usually raised on in the conventional part of reservoirs. Then we'll talk about the laboratory confirmation of unconventional gas reservoirs. Once we define this or identified it, then we have to confirm this from some lab confirmation. There are rules for the lab confirmation that will help us identify the potential of the unconventional reservoir to be a gas reservoir. Once we understand the conditions and how we can confirm it, then it comes to time, how can we develop it? Okay. So the development of gas reservoirs will depend on the evaluation wells. We'll talk first of all on evaluation wells. What's required in evaluation wells? How do we do this? Then from the evaluation wells, we'll talk about drilling and completion of unconventional reservoirs. That includes both the gas and the oil. Then we'll leave some time for the questions and answers. Okay, let me start with the shale reservoirs in brief. Okay, shale reservoirs in brief, guys, I'll put it in one single sentence. And please don't forget the sentence at all. What is shale gas, or what is shale reservoirs in general? Shale reservoirs are go get the hydrocarbon from the source rock before it migrates. That's simply what is unconventional reservoir all about. I will not gonna wait for the hydrocarbon to leave the source rock and try to migrate up and try to find a reservoir and a trap to create a conventional reservoir. I'm not gonna wait for this. Because if you do, you will lose a lot of your hydrocarbon that may not find a reservoir or may not find a trap. So this is really a bad choice if you leave the hydrocarbon to migrate again, like we had before. In our conventional reservoirs, it's actually happened millions of years ago when the hydrocarbon was generated originally in the source rock. Then it left the source rock, migrated up. And we looked at it before in the previous lecture, and we found that we lost almost 90% of the hydrocarbon that left the source rock is gone. And we only have 10% that succeeded to find a reservoir and a track. Okay, so we're not gonna do this again. So simply, what is unconventional reservoir, guys? It's simply go get the hydrocarbon from the kitchen, get the hydrocarbon from the source rock before it migrates. In this case, you can get it all without losing anything of it. So that's simply what is the unconventional reservoir. That's why the unconventional reservoir hydrocarbon in place is huge. Okay? It's huge because you're talking about something that did not leave and was not lost. It's still there, trapped inside the source rock, and we need to go and get it. Okay, so if anybody asks you about what is the unconventional reservoir, it's actually getting the hydrocarbon from the kitchen, from the source rock itself. Okay, facts to never forget also about unconventional reservoirs. The first is shale reservoirs are not clay minerals. We all confuse clay with shale. Okay, clay is a shale. Yes, that's true, but not every shale is clay. Think of it of a family. It's called Shale family. Shale family has multiple members. One member of this family is called clay. The other members are not. Okay? So the shale is a big, huge family based on grain sizes. Anything, any rock that has grain sizes between 0.001 to 0.004 millimeter is considered geologically as a shale, okay? Regardless what is the composition of this rock. Clay is one of these members, okay, or one member of this family. So clay is a member of this family. So not every shale is clay, okay, but every clay is shale. So this is one very important fact. Never ever think of producing hydrocarbon from clay. That doesn't happen and will never happen. Clay will never contain hydrocarbon. Okay, so in this case, shale is not clay. Okay? This is a fact. You have to keep it in your mind. Second, shale reservoirs are normal reservoirs, clastics and carbonates. Okay, shale is clastics and carbonates. So what is the difference between this and the conventional reservoir? Going back again to the definition of the shale family. Definition of the shale family: any rock that has grain sizes between 0.001 to 0.004 millimeter is a shale. So if your sandstone grain sizes is between these two numbers, or your carbonate grain sizes is between two numbers, your clastics and your carbonates are considered shale. Okay, so shale is not clay mineral. It's anything between the geological definition of the word shale, which is grain sizes related between 0.001 to 0.004 millimeters. Okay. Here are examples from the globe. Here is an example from the US. This is the Eagle Ford, one of the most famous unconventional reservoir in the US. And you can see here, it's actually carbonate, limestone with some clays. Normal reservoir is not clay. It's a reservoir that has percent of clay, very normal like any other reservoir. If you go to North Africa, this is calcareous sand. You have sandstone with some calcite. So this is a calcareous sand with some clay minerals as well. So it's a normal reservoir, but this reservoir is shale because of its grain sizes. If you go to the Arabian Gulf, very nice, clean limestone. Okay, but it is shale. Why? Why is shale is not normal conventional reservoir? Because the grain sizes is between 0.001 to 0.004. So what will happen if my grain size is between 0.001 and 0.004? Properties will change. The properties of the rock will change, okay? And that's what we will discuss today. What are the properties of the rock and what are the properties of the hydrocarbon, okay? Okay, Third, shale reservoirs have very low permeability. So this is one of the properties. Yes, it's a limestone. Yes, it's a sandstone, but it's not a normal limestone sandstone with the normal permeability range that we are used to. No, its permeability is in the nanodarcy, very, very, very low permeability. Okay, here is an example how we put this as function of permeability. All reservoirs now, guys, are classified as function of permeability. If your permeability, if you are in the conventional reservoir, your permeability range will be in this box, down to millidarcy, up to darcies. So in the conventional reservoirs, you can have reservoirs up to darcies, depends on fractures and other things that makes the permeability much higher. Down to millidarcy. So anything that's down to millidarcy, all the way up to darcies are considered conventional. Okay, because the grain sizes will be more than 0.004. It's not going to be within the range of 0.001 to 0.004. If you go to the unconventional part, then you move your sandstone, limestone, and dolomite to this part of the permeability, which is in the microdarcy and the nanodarcy. So if you are in the microdarcy permeability or the nanodarcy permeability, you are not a conventional reservoir. You don't have a conventional reservoir. You have unconventional reservoir. But we come here and we put a separator between the microdarcy and the nanodarcy. The microdarcies, we don't call them shale, we call them tight reservoir. So you know the tight gas reservoir, you know the tight oil reservoirs. So the tight gas and the tight oil are normal reservoirs that has permeability in the microdarcy values. But if your permeability is in the nanodarcy value or range, then you are in the shale. So you can see the classification now. Everybody now classifies all reservoirs according to permeability. So if your permeability in the order of millidarcy all the way to darcies, you are in the conventional reservoir. If you are between microdarcy to nanodarcy, you are in the unconventional reservoir. But if you are in the microdarcy, you are in the tight unconventional reservoir. If you are in the nanodarcy, you are in the shale unconventional reservoir. I hope this is clear now for everybody, because that's a confusion in many minds that actually I talk to many sometimes. Here is an example of core analysis from North Africa. If you look at the permeability here, the permeability here in 0.0000102, for example, millidarcy, it's very, very low. This is a North Africa example, shows an unconventional reservoir and actually measured lab permeability, 0.0000 something of a millidarcy. So it is in the nanodarcy type permeability. So permeability has to be in the nanodarcy for this rock to be called unconventional reservoir shale. If you are in the micro, it's unconventional reservoir, but it's unconventional reservoir tight gas or tight oil. Okay. Right. So this is the third fact. Okay, these are facts that please never forget this. This will put the stage or set the stage for the definitions of unconventional reservoir. The other very important thing, that shale reservoir may or may not have porosity. That raises a huge question mark in the mind of everybody. Actually, it actually makes your eyes and blows. How come? How come I have a reservoir that does not have porosity? That raises a huge question in your mind. Where does the hydrocarbon live if I don't have porosity? We've been raised all these years that our hydrocarbon lives inside pores. Okay, that's not the case, guys, in unconventional reservoir, and that's what we need to understand today. Where does the hydrocarbon live? It's an important thing that we need to understand. The hydrocarbon or the unconventional reservoir does not rely on the existence of porosity. If you have some porosity, this is good news. If you don't, that's not even a blink. Don't even mind that I don't have any porosity in unconventional reservoirs, okay? So as I said, it's an eye-blowing. So now what is this? Here are the examples from many fields in North America. Here is the Marcellus, for example, the Haynesville, the Woodford, the Fayetteville, Eagle Ford, Barnett. Look at the range of porosity here. For the Marcellus, the one of the most famous, from 4 to 10 pu. Average is about 5 pu. Does 5 pu makes a reservoir in conventional arena? No. 5 pu will never make a reservoir. It's not going to be economical. Okay, but 4 to 10 is a huge reservoir in Marcellus. Look at the original gas in place here in TCF, trillion cubic feet. It's 1500 TCF. Huge original gas in place. Huge. Where does this huge hydrocarbon live? If I have only from 4 to 10 pu, this means that the porosity is not what we are after. We are not after porosity. So if you look across here, you don't see much of it from 8 to 15, 3 to 9, 2 to 8. That goes all over the place. That's not only in North America, it's everywhere. If you look at as I said, the original gas in place, you know what 1500 TCF is? It's huge reserve. I remember, for example, in Egypt, when they discovered one of the biggest fields in the Mediterranean, it was 50 TCF. And everybody was saying, huge discovery. 50 TCF. We're talking here about 1500 TCF. Huge. Now, if we even have 10% recovery, then what is your reserve? Your reserve will be 150 TCF. Huge reserve. Okay. So that the low porosity here does not justify a place for this hydrocarbon to live. So the hydrocarbon does not really rely on porosity in unconventional reservoirs. So we need to understand what's really happening there. Where does this hydrocarbon live in the unconventional reservoir? Okay. Here is also another example from North Africa. Here is actually a field that we took so many plugs from the core, and you look at the porosity 5, 4, 6, 3, 2, also all of this very, very, very low porosity. So it's not really, porosity is not the one that you judge the economics of unconventional reservoir. Unconventional reservoirs are not judged by porosity. If you have porosity, this is really good news. But if you don't even blink. That doesn't make any difference, right? So as I said, shale reservoirs may or may not have porosity. That raises a huge question. Where does the hydrocarbon, gas, or oil live? And that's what we need to understand in few minutes. Right? Let's understand that. When you really understand that, we need to understand the unconventional rock structure. What is the unconventional rock structure? First of all, here is an outcrop of unconventional reservoir. If you look at this unconventional reservoir, just by the first look, it's very clear. It's actually a group of laminated rocks. Look at all this lamina, very, very thin lamina. So you can see the lamina is going to this direction and that part. And also there see a lot of lamina in here. You can see all this lamina also going in that direction. So one of the most important characteristics, guys, keep this in mind. One of the most important characteristics of any unconventional reservoir that's structured by very thin lamina. This is one of the properties of unconventional reservoir. Has to be very thin lamina. Okay, so just keep this in your mind. Okay, how does it look like on the logs in this case? If you can see the rock now at the outcrop on the surface, how does it look down home? Well, here is an example of unconventional reservoir from the Middle East, from the Arabian Gulf. Here is the gamma ray. Let's just blow this gamma ray a little bit to make it bigger. Here is the part of the gamma ray. Look at the gamma ray. This gamma ray goes back and forth, back and forth, back and forth. What does it mean? It means it's huge lamina, clear lamina. If you don't see these characteristics on the unconventional reservoir, walk away from it. It has to have this lamina. Okay, so one of the properties of the unconventional reservoir, it's highly laminated, highly thin laminated reservoir. So the lamination has to be high lamination. If I take the same zone and I look at the resistivity, clear lamina. Resistivity goes back and forth, back and forth, back and forth. That's what the lamina structure on the logs look like. So also, gamma rays shows lamination. Resistivity shows lamination. Even the neutron density that normally doesn't show lamination because of the resolution of the tools, the neutron density also show lamination. So one of the most important characteristic of any unconventional reservoir, it has to be thin laminated reservoir. If you don't see this in a thin laminated reservoir, in unconventional reservoir, you don't call it unconventional reservoir, okay? So one of the most important property of unconventional reservoir has to be laminated, okay? So where, again, we didn't answer the question, where does the hydrocarbon live? Just wait for a second, okay? All right. So being thin lamina is a characteristic. Then where does the hydrocarbon live? Here is the answer. Well, the hydrocarbon is released from the organic material that lives in between the lamina of the rock. So that's how the organic material was originally deposited or originally buried, let's put it that way. So the organic material are buried between these layers. So the organic material lives between these layers. So between these layers, you can see organic material, which we call it kerogen. So the organic material lives between these layers. So it doesn't need pores. It actually creates hydrocarbon that lives between the layers. That's why it's huge. Okay, layers are huge in space. Okay, lateral extension. That's why you have 4 to 5 pu and you have 1500 TCF, because that TCF does not need the 5-6 pu. It lives between the layers. Okay, so the hydrocarbon is created in the source rock and lives between the layers. Okay, so the hydrocarbon is released from the organic material and lives between the thin lamina and is trapped there. So it doesn't need porosity. That's why when we started saying, if you don't have porosity, don't even blink. It doesn't matter. Okay, because that's not what we are after. We are after the lamina, because our hydrocarbon lives between the lamina in the source rock structure. That's by the definition of the source rock. It's highly laminated rocks. Okay. All right. Is it oil or gas now? Now we understood. Where does the hydrocarbon live? It lives between these lamina. Okay. Is it oil or gas? Because you need to go back to the history. Okay. What are the conditions that these organic material were subjected to? Okay. So is it oil or gas? It depends on the condition. Right? The condition is mainly the temperature. Now, if the source rock was subjected to temperature between 60 to 120, that's an oil producer. If it is from 120 to 150 degrees centigrade, that's a gas producer. So if your source rock was subjected to temperature between 120 to 150 degrees centigrade, that's what we call gas window. So when you have gas reservoirs, you need to know that millions of years ago, across the time, where the hydrocarbon was cooked inside the source rock, the temperature there was from 120 to 150. For sure, we are all engineers. We know there is nothing in nature discrete. 120 can be 110 or 105 or 125. Don't be too discrete. Not 120, 119.5 doesn't work. Okay, we are engineers and we know there are ranges of things. So between 120 to 150, that's the gas window. So I know if I have the history of my source rock, that my source rock was subjected to temperature between 120 to 150, then my source rock will generate gas. Okay, that also raises a question. Okay, this process that we call this process desorption. So the hydrocarbon is generated in the source rock by a process called desorption. The hydrocarbon that you have in your conventional reservoir was originally desorption, then it migrated up and lived inside the pores. So living inside the pores was an after the fact process, after the generation and the migration. But everything is originally generated from desorption inside the source rock. If it didn't leave, it's still there. If it left, it will propagate up because of the gravity. Then it lives in the source rock and get trapped. I'm sorry, in the reservoir and get trapped. So the process is called desorption. Let's understand a little bit the desorption. It's from the chromatography. I'm sorry, the chromatography, the chemical analysis of the kerosene. Okay, what is the chromatography? Chromatography is actually tells you how things are happening. Desorption, by definition, from the chromatography, is the release of one substance from another. Okay, so the release of hydrocarbon from the organic material. The release of hydrocarbon from organic material is called desorption by definition. So either from the surface or from the substance itself. Desorption can occur when the equilibrium is altered. It means when there is a change in the equilibrium due to pressure and temperature. When you have a change of equilibrium due to pressure and temperature, that release happens. By the way, you see this in every day. You see this every day, but we don't pay attention to. For example, if you have a glass of water, this glass of water at the surface, you have the water here, and above the surface is the air. Air has oxygen, water has oxygen. There's an exchange of oxygen between the air and the water that you don't really see. That's what's called desorption. Oxygen can get released from the surface of the water up, and the oxygen from the air can actually goes down. That's transfer between these two surfaces is what what the desorption is all about. Oxygen in this case is a desorption. Oxygen is desorbed, is getting out of the water, going to the air, going from the air down to the water. That process happens in every single day. Okay, so the desorption that we see in normal life is exactly what happened downhole. That our organic material, the hydrocarbon got released from this organic material due to the unequilibrium situation, due to the pressure and temperature. That release of hydrocarbon is trapped between the layers of the source rock. Okay, so that's how the hydrocarbon is created. When can we find gas at a certain temperature from 120 to 150? Where does it live? It lives between the layers. Does it need porosity? No, it does not need porosity. And that's why it has huge volume, because it's not trapped in a very small fraction of a rock. It's actually trapped inside a huge layer that's laterally extended. Okay. So if you go to any book and you start to read the definition of the shale reservoir, here is what you see. Shale is a fine grain sediment. We agreed on this. Fine grains because it's between 0.001 to 0.004 millimeter. So you don't actually memorize it. It's very easy to understand. So it's fine grain because it's from 0.001 to 0.004 millimeter, whose original constituents are organic material. Okay, so it's organic material that's the constituent, and the organic material is the one that will create your hydrocarbon, and characterized by thin lamina. We saw the thin lamina, and we understood that the hydrocarbon lives between the thin lamina. Also, we saw that the lamina is indistinguishable bedding planes. We saw bedding planes in different directions. It doesn't have to take the same direction. Actually, it's always random direction. Within few feet, you see multiple directions of this thin lamina, because at the time of the deposition, which was actually completely disoriented. Okay, so that's how we see these definitions, and that's how we took one of them at a time, and understood why the geologists defined the shale the way they defined it. It has to be thin, it has to be fine grained, has to be thin lamina, has to have organic material, and the bedding characteristic is absolutely indistinguishable, and it's a random distribution. Okay. Okay. The generated hydrocarbon, is it oil or gas? We said, well, it actually depends on what happened a million of years ago. If million of years ago was subjected to 120 to 150 degrees centigrade, it will produce gas. Well, sometimes we don't really know what happened millions of years ago. Is there a different way to find this out? Yes, there is a different way. We do it in the lab. So in the lab, we can find out if my source rock will produce gas or will produce oil. We rely on something very important. We call it VR, or vitrinite reflectance. I will spend some time on this actually, and also, have some slides at the end. If we need some more elaboration on this, I will be happy to do that. But I will give you an idea what is the vitrinite reflectance. From the word reflectance, we understand there is a reflection somewhere. Reflection of what? Reflection of light. We send light on the organic material, and we look at how much of this light will be reflected, as simple as such, with certain steps that we do based on the ASTM. Everybody knows that we have an ASTM, the American Society of Testing and Minerals. The ASTM put rules in the way we do lab measurements. So ASTM has rules of how we measure the vitrinite reflectance. So the vitrinite reflectance idea is, if your material, if your organic material is capable of producing hydrocarbon, it has to be soft. The hard organic material will not produce hydrocarbon. Just keep this in your mind. For the hydrocarbon, for the organic material to produce hydrocarbon, it has to be soft. We call it maceral. As I said, if we really need more elaboration on this, I will spend some time at the very end. But from the basics of what is the vitrinite reflectance, the property of the organic material to produce hydrocarbon is to be soft, moist. It has to be moist, soft. Okay. If it gets harder, it will not produce hydrocarbon, right? Or it already produced the hydrocarbon and it's gone, right? So now, if the material is soft, will it reflect the light? No, it will not. How about if it's hard? It will reflect. So depending on being soft or being hard, the reflectance will be different. So we actually measure the reflected light. If the reflected light has a certain value, we actually call it a source rock that will produce hydrocarbon. Okay, and if it reflects at a certain percent, it produces oil. At a different percent, it produces gas. If it reflects higher than this, it will be producing. So as I said, the vitrinite reflectance is actually how much, or the ability of the organic material to reflect the light that we put there. If the material is soft, moist, it will not reflect much. If it gets harder, it will reflect more. By measuring the reflection of this material to the light, we actually can find out if it's producing oil or it's producing gas. Okay. It is actually a flow chart, huge flow chart, but I'm not gonna, talk about it unless you guys need to talk about it at the end, because we have some material here to cover. Here is the part that we call vitrinite reflectance. If the reflectance is between 0.25 to 1.2% of the light, that's an oil producer. If it's 1.2 to 2%, that's a gas producer. If it's above 2%, no hydrocarbon whatsoever. It's getting harder, and it will not produce any hydrocarbon. So the vitrinite reflectance is a measurement of the reflection of light. If the reflection of light is between 0.5 to 1.2% of the light, that's oil producer. So this is a kerosene that will produce oil. If it's between 1.2 to 2%, it's a gas producer. If it's above 2%, it's actually no hydrocarbon whatsoever. How can we do this? We actually have this apparatus, which is a microscope. You put the organic material here somewhere, After you prepare it as the ASTM asks us to prepare, you grind it and you do it like pellets. So we, as I said, we're not going to talk about this today, but you actually prepare the sample with the guidance of the ASTM guidance. You put it under this microscope and you send the light and you receive the reflection. Okay. Then here is the grading. The grading goes between thermally immature, oil window, wet gas, dry gas, absolutely mature, thermally over mature. If I take this part and I blow it again, here is the section that we are interested in. If we are talking about gas reservoir, shale gas. If the reflection between 1.1 to 1.3, that's a wet gas window. So if the reflection between 1.1 to 1.3% of the incident, this is a wet gas window. From 1.3 to almost 2, okay, it's actually a dry gas window. So we identify the type of hydrocarbon in the laboratory. That reflects what happened millions of years ago. This means my source rock was subjected to 120 to 150 degrees centigrade at the time of the production of the hydrocarbon. Okay, so we do this in the laboratory based on the ASTM rules, based on the kerogen sample that we take out of our source rock, put it under this microscope and measure the reflectance. That's what they call it, vitrinite reflectance. The reflectance of this light over the organic material. If the reflection from 1.1 to 1.3%, that's a wet gas zone. From 1.3 to about 2 to 2.2, that's actually a dry gas zone. So we know the production of the organic material from the source rock based on the property of the kerogen of the source rock. Okay? All right. So that's how we define our reservoir, our hydrocarbon, where it lives, okay, and what type of hydrocarbon I will be expecting from what's happening in here. Okay. So what is the hydrocarbon volume? How can I calculate the hydrocarbon volume? Guys, I need you really to pay attention to this part because this is very important part. How much hydrocarbon do I have? How I can figure this out? Again, always relate what you learn from the conventional reservoir to the new definitions of the unconventional reservoir. Let's just go visit the conventional reservoir first. To look at the hydrocarbon volume in any conventional reservoir, we actually define two S's. We have very well-known two S's. We have the first one called SW. Okay, Mr. Archie did a great job in defining this, and other people came up with doing some more work on trying to find SW, which is the percent of water in our pore space. Okay, and the second S is my S hydrocarbon, which is simply 1 minus SW. That's what we are raised on, okay, in our conventional reservoir. We all calculate with whatever model we use to calculate SW. Then 1 minus SW is the volume of my hydrocarbon that lives in my pore space. Okay, that's not the case, guys, in unconventional reservoir. In unconventional reservoir, we have 4 S's, not 1, not 2. Okay, we have 4 S's. I need to pay attention to this again. Okay, so unconventional reservoir don't have only 2 S's. We have 4 of them. For sure, the first one is the same, SW. The amount of water in my unconventional reservoir similar to the conventional one. But when it comes to hydrocarbon, we have 3 S's. We have S1, we have S2, and we have S3. Actually, when I teach this in my classes, I say, since we consider the source rock is our kitchen, and pay attention to this, since we consider our source rock is our kitchen, then let's just go to the kitchen and see what type of food do I have in my kitchen. Actually, you have 3 types of foods in your kitchen. One of them is already cooked and you can eat now. The second part you put in the fridge, which is actually ready to get cooked. It's not cooked yet, but you can cook it. Okay. The third one is one that's exposed expired and you cannot use anymore. Okay, you have three types of food in your kitchen. One of them is already cooked. All you need to do is just sit down and eat it. Second is something that you need to cook to be able to eat. Third is one that's already expired and is very dangerous for you to eat. That's exactly what you have in the source rock. You have S1, which is the hydrocarbon that's already generated and lives in the source rock. It did not leave yet. It did not migrate yet. It's already generated and it actually is trapped inside your source rock. The second one is the amount of corrosion that still exists in the source rock, that if you leave it for some time, it will create hydrocarbon. We call this S2. So S1 is the amount of hydrocarbon that's ready to use now, ready to get. S2 is the amount of hydrocarbon that if you cook it, you will get. S3 is the amount of hydrocarbon that you lost. What do you mean hydrocarbon that I lost? This is something very important. Okay, let's just take it one by one first. So you have S1, S2, S3. S1 is the hydrocarbon released and trapped in the source rock now. S2 is the potential of the organic material to produce more hydrocarbon. So what is S3? S3 is bad news. Bad news in your kitchen that the food is expired. This is bad news. No longer of benefit to you. Okay? This is the same thing. What is hydrocarbon? Hydrocarbon is hydrogen and carbon. What if your carbon is used in another process other than hydrocarbon? What do you mean by that? Well, if your source rock was subjected to oxygen, okay, if your source rock is subjected to oxygen, oxygen will react with carbon and create CO2, carbon dioxide. Now you lost your carbon. Okay, your carbon is gone, and you lost that carbon to CO2, that is not hydrocarbon. So if you have, by any chance, an environment that's actually oxide, okay, we call it anoxious environment. That environment that has oxygen in there, if the oxygen is enough to react with the carbon and create CO2, that's really damaging to your reservoir. That's an expired carbon that you have no way to get it. So the S3 is the hydrocarbon lost due to CO2 release. So we have three S's. S1 is ready to use now. Now, if you drilled in the source rock, you will produce S1. If you waited for another million of years, you will produce S2. S3 is something gone, expired, no use for it. You have CO2, and we are not really drilling for CO2. Okay, we drill for hydrocarbon. So that instead of having one S, as we usually have in the conventional, in the convention is actually this S1 that already migrated, left and went and lived in the pore space. That's the S1 that's left from the source rock and migrated up. The remaining of the S1 is still trapped in your source rock and is ready for you to go and grab. So when you drill for the source rock, you will produce this S1. S2 needs time, S3 is gone, no use for it. Okay, so if you go and do any analysis, or you look at any analysis in any unconventional reservoir, you will find S1, S2, S3. So now you guys know what S1, S2, S3. S1 is the amount of hydrocarbon that if I drill today, I will produce that one. S2 is the potential, the ability of the source rock to produce more. S3 is very bad news. If I have high S3, that's a very bad quality source rock. I need a source rock that has the least S3. It means it doesn't have enough of free oxygen that can actually take away my carbon and create CO2. Okay, so in our unconventional reservoir, we have four S's: S1, S2, S3 plus the SW that we normally have. Okay. All right. Now, if you look at the decline curve, regardless of gas or oil, what is the decline curve in unconventional reservoir? If you look at the decline curve in unconventional reservoir, now we have to go back and say, do you have a little bit of porosity or you don't? If you have a little bit of porosity, this porosity that you have in the unconventional reservoir, as I said before, we don't really care. But if you do have, that's fine. So if you have some porosity, some conventional porosity, you will follow the conventional decline curve. What is the conventional decline curve? High production at the beginning, fast decline. That's what the conventional decline curve is all about. High production at the beginning, fast decline curve. What is the decline curve of unconventional reservoir? Unconventional reservoir has low production but sustained for many years, goes up to 30 to 40 years. So if I compare between these two, I start with the conventional intergranular, even if you have some of them. So the intergranular porosity will actually give you this decline. This is the conventional decline curve. High production, rapid decline. For the other part, which is the unconventional organic production, which one of the S's? It's S1. Which one of the S's that you will produce? You produce the S1. So S1 will be low production, but for a very, very long time with a very, very steep decline curve. As you can see here, is sustained for a very, very long time, and the combined conventional and unconventional will give you the total production from the unconventional reservoir. Okay, so this is the normal decline curve. It stays for a very long time. That's why the lifetime of an unconventional well is much longer than the lifetime of a conventional well. Okay, all right. Now, how to produce this hydrocarbon? Well, we started with the understanding. From the understanding, you can plan of how you produce the hydrocarbon. Okay, so let's just start from the understanding to go to the planning of how to produce this hydrocarbon. Let's just go for the review the facts and then make the decision. So we have facts and decisions. The first fact, the facts are unconventional reservoir structure. They are thin lamina. It's one thing, thin lamina. Hydrocarbon is dissolved between the layers. Little to no porosity. These are facts. Okay. Now, if you think about these, can I drill a vertical well in thin lamina? Well, how can you perforate? You cannot actually drill a vertical well and perforate for many reasons. Drilling a vertical well and perforation, you cannot really make sure that your perforation will be in the zones of production. They are very thin lamina. You will be shooting blindly. Okay. Second, your reservoir, it actually lives in layers. How can you produce layers from a vertical well? Layers means extension, lateral extension. So this means you have to do this in a horizontal type drilling. Why? Because we understood that it's actually lamina, laterally extended. My hydrocarbon lives between this lamina. Then I have to go laterally and try to connect this lamina together. And that's why everybody's saying you cannot produce unconventional reservoir unless you drill horizontal long reach, go as long as you can, and make multiple fracs to connect these layers together. That's from the understanding. Our hydrocarbon does not live in pores. Our reservoir is very highly laminated. Okay, drilling vertical wells and perforation, that's not a way at all. It's not going to be a good way of producing these reservoirs because we are in layers. Then you have to put your well between the layers, then you connect the layers above and below. Okay, so that's the only way of producing these unconventional reservoirs. So conventional well design of vertical wells and perforation will not work. That's by our definition. That's from the facts that we know. Second, horizontal drilling is a must. Why? Because you need to go between your layers, stay there as much as you can. Okay. Third, long horizontal well. Third, you need to hydraulic fracturing is the most suitable completion method applicable for these reservoirs. So these are from the facts that we learned, we understood how to handle these reservoirs. What are the decisions that need to be made for these reservoirs? Okay. So let's assume that I have this reservoir right here. Here is my unconventional reservoir. We have steps actually through the unconventional reservoir. The first step is to evaluate this reservoir. Evaluation of the reservoir is knowing the type of hydrocarbon, knowing the type of the lamina that we have, knowing the thickness of our reservoir, knowing the quality of our reservoir. We do this through drilling the first vertical well. So the vertical well that we drill in this reservoir is not for production. The vertical well that we drill in this reservoir is for evaluation. So we drill a vertical well first to get core, to collect data, to understand the reservoir. Okay, so the first step is to drill an evaluation well. Evaluation well is a well that we understand the reservoir from. Evaluation well is if you go for efficient well construction, drilling a vertical well in there. Here is the vertical well that we drill to evaluate. When you evaluate, you need to do coring and core analysis. Do what we call the pyrolysis. Pyrolysis means you measure S1, you measure S2, you measure S3, you measure total organic carbon, you measure hydrogen index, so many things that you need to measure. One of the three most important are S1, S2, S3, because that relates to your production. So you do coring or cutting, and you do the measurement of pyrolysis. Here is the evaluation of the properties of my reservoir. Okay, then you do some logging. From the logging, we understand the properties of our reservoir. So we do logging there, and we do log analysis at the same time. So here is the logging that we get from the vertical well. I'm not doing the vertical well for production. Give this in your mind, guys. We do not do vertical wells for production. We do vertical wells only for evaluation, for understanding. Okay, so do the petrophysical analysis of this reservoir. From the petrophysical analysis, we calculate the S1, we calculate the S2, we calculate the S3, we look at the total organic carbon. We do a lot of evaluation. We look at the properties. We make sure we can see the lamina. You can see the lamina there very clearly. Make sure the lamina exists. So that's actually put properties of your reservoir. So from the evaluation well, we take core, we look at logs, we sit down and evaluate our reservoir. Okay. Once we evaluate it, we're not gonna leave this vertical well unused. We can actually go there and drill a horizontal well from this vertical well. Okay. Then once we understood our reservoir, we need to go there and say, okay, drill a horizontal well. Either from the beginning, now after you drill the vertical well, or from the vertical well. Don't leave the vertical well unused. You go there and you actually use a web stock that we normally used in the past. We don't do that much these days, but we go with a web stock, and from the web stock, actually we go and drill the horizontal section. Okay, we drill a horizontal section in there. Stay as long as you can. Use the LWD data that you have. Make sure you stay in your reservoir. Make sure you are between the layers, okay? Then you decide on your completion. The completion of these unconventional reservoirs are doing multiple stage frac. Doing multiple stage frac. So you do the completion that you have there, okay? You complete this well by optimizing zonal isolation and doing the multi-stage frac. So you actually put there, you put either whatever the methodology. I'm not going to talk about methodology because I don't want to talk about service companies, certain type of operations. But the whole idea is you actually look at here, and you at every zone that you have, you start applying stimulation, and you do multi-stage fracturing. Here are the multi-stage fracturing that you have. The thing that this frac will do will connect all the layers up and down, all the layers up and down, and production be from all the layers into this horizontal well. So this is the way to produce your unconventional reservoirs. So unconventional reservoirs are not produced by single well and perforation. It doesn't work. Why? Because we understood from the properties of the unconventional reservoir that these reservoirs are thin lamina. You cannot do thin lamina production from vertical wells. These reservoirs are laterally extended. Then you have to make sure that you expose your well to a lateral extension as much as you can. We know it is actually thin lamina, so we have to connect the lamina together by doing this multiple stage frac. Okay, so the way we produce these reservoirs is by horizontal wells, multi-stage frac. Either we are to have different type of multi-stage frac. As I said, I'm not going to talk about this because I don't want to talk about certain operation for certain service companies. Okay, all right. So to summarize this unconventional production process, number one, drill an evaluation well. From the evaluation well, it will be a vertical well. That vertical well, you acquire all the wireline logs. You actually take the quad combo advanced logs, all the logs that the petrophysicist and the evaluation guys will ask you to acquire for the evaluation of the reservoir. Okay, then you complete the analysis of the wireline and the core data. Okay, use available cutting and core data, and you do the measurement. In this case, do the measurement for the available cuttings and core data. Okay, then you calculate the TOC, the S1, the S2, the S3, all these values that you have, right? Then you drill a horizontal section. That's for production. Use a OP stock for the if we're gonna use a vertical well, or you go directional from the beginning. Okay, drill the horizontal section, acquire LWD data on the fly to make sure you put yourself in the proper zone. Well completion is very, very important, which you do it multi-stage fracturing, and this multi-stage fracturing will connect all these layers together, and this is the way to produce your unconventional reservoirs. Okay, thank you very much. Up to this point, I think I covered what I needed to cover for this lecture, and I'm waiting for any questions and answers. If the guys are more interested of how we do the veterinite reflectance and all these definitions of the flow chart I showed before, I'll be very happy to spend some more time also on this as well. Okay.
Thank you, Dr. Mustafa, for this super informative webinar. I'm sure we all benefit greatly from it. And now for the Q&A session. First question. Is there communication between the lamina and could the gas oil flow from a lamina layer to another?
Yeah, sometimes it does. It depends on how thin the lamina are, but actually that's not of interest to you because that's not going to affect the way you look at this thin lamina. It's not going to affect the way you drill. At the end, you will put yourself in a horizontal section. You connect the multiple layers by fracking. So either it's connected or it's not connected. That's not going to really affect your decisions. Sometimes it actually does, but that's not going to make you or change your mind to complete or drill a well like a vertical well or even slanted wells to produce these reservoirs. Yeah. It's not going to change your mind.
Okay, and another one is according to unconventional reservoir decline curve, it stays sustainable through the years. Does that mean we don't need to use simulation methods to extend the reservoir life?
Simulation, when you talk about simulation method of how you estimate the lifetime of a well and this kind of stuff, I tell you the truth, I don't think we're still at the early stages of doing this type of simulation for the unconventional reservoir. I can assure you that nobody can claim 100% that we really know what's happening in the unconventional reservoirs. Plus, the properties of the unconventional reservoir is so complicated. Permeability distribution in unconventional reservoir is so complicated that it will be a real challenge to figure out how to do a proper simulation of this unconventional reservoir. I can see your point, which is a very, very valid point, but it's so difficult. We have difficulty actually of simulating conventional reservoir when you see variation of permeability, and we have to go for tensor perm for this, and add to this the complexity of being thin layers with a huge, very, 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 very low permeability like nano Darcy. That will be a real challenge. Okay.
Okay, and our last question. What if the starting materials are plants? Will oil be produced in the oil window from 80 degrees to 120 degrees?
He's talking about the plants that were actually buried in there, right?
Yeah.
Okay. Well, that will take me to, as I say, if guys need to understand this is in full, we need to understand what are the corrosion. Okay. Corrosion actually are divided into three types. The first type we call it leptonite. Second type we call it vitrinite. Third type we call it inertinite. Okay. These three types actually vary in the composition. For example, for the leptonite, it has to have more of lept, which is like a fat type part of the plants, and also like it has to have like alga, either blue alga or green alga. So it actually it goes back to marine type deposition. Okay, the leptonite by definition it's more prone to produce oil. The second type, which is the vitrinite, which is mainly composed of branches, roots, leaves, all of these type of forests and wood. This one is prone to gas. Okay, so it actually depends on what type of organic material you have, plus what is the temperature that was exposed to, that will make both the oil and the gas. So the leptonite, it can actually be a very high potential of oil with some potential of gas. Vitrinite will be very high potential of gas with some potential of oil. Inertinite is the one that we talked about here. If you are in an environment that has free oxygen, then the carbon will be all taken by the CO2, and you get some inert. And you know what the word inert means? It's not going to produce any hydrocarbon. So the inertinite is more taken away. The carbon is more taken away by the CO2. So these are definitions of corrosion. As I said, I don't want to go through all of these details. It's not really gonna help you as an engineer who was just introduced to unconventional reservoir. But yes, there are the type of the organic material, the deposition, the temperature, the pressure are all included in the way we look at the hydrocarbon potential and hydrocarbon type. Okay, right?
Thank you. Thank you so much, Dr. Moustafa, again, for your effort in this terrific webinar. Now, to highlight, this session has been recorded and will be uploaded soon on BioPetro YouTube channel, so kindly make sure to subscribe to our channel. Wishing you a great day, stay safe, and bye.